So just as a quick review of last week we talked about the Navier-Stokes equations, and we ended our last class trying to derive some equations for flow between two infinitely long parallel plates. I guess I'm not gonna go into too much detail because we already did this solution last week, but we actually ended up with several constants that we haven't solved yet. So just as a quick review, this was flow traveling between two infinitely long plates. So these are two plates. They're very, very long, right? They're infinitely long. We said that the distance between the plates, I think we called it A, if I remember correctly. I could be wrong, but I think the distance between the plates was called A. We said that the fluid traveled in this direction, which means that there has to be some sort of pressure gradient acting on the fluid. So we know that there's a pressure gradient, which is a pressure on one side, which is greater than the pressure on the other side. And we also said that this top plate was moving with a constant velocity of capital U. Of course, you know from the no-slip condition that the fluid particles in contact with this plate are going to move along with the plate, which means that both the pressure gradient, this plate movement, and the force of gravity, which you know acts in the vertical direction, all of them are going to be influencing the movement of the fluid. And we wanted to find an equation that describes that fluid movement. Now, what we did was essentially, given our parameters, what we did was find an exact solution to the Navier-Stokes equation. Of course, finding exact solutions is only easy if our system is very idealized. For more realistic systems, it'll be harder. But at least this gives us an idea and some practice on how to solve these systems. Now, you know I'm not a fan of like these recipe type problems where step one is this, step two is that. I don't like that because I feel that if we get too used to that, we're going to just become like little drones that just follow steps without knowing what we're doing. However, and it's a big however, I think that for many of these types of problems, I do think that there's at least three things that we need to understand in order to solve this problem. So whenever you get a problem where you're given a flow situation and you're asked to derive an equation that describes the motion of that flow, I would recommend that we first start by describing our system. And when I say describe the system, what I mean is take everything that was given to you in the problem statement and take everything that you can deduce from that problem statement. So right now, we're told that we have gravitational force, we have a pressure gradient, so that's forcing fluid to move in this direction. And then we have this movement of this top plate. So given all that information, how can we describe the system? Well, if we were to set our axes, let's call this X, Y, and then Z would be normal to the paper, so in the direction pointing towards you. What can we say? Well, we know that because these are infinitely long plates, and because everything is uniform in this direction, you notice that pressure only acts in this direction. Gravity only acts in this direction. So there seems to be no force, and by extension, no movement in the Z direction. So what we can get from this description of the system is that our velocity in the Z direction, which we call W, is 0. There shouldn't be anything in the Z direction. We can also say that any changes in the Z direction would also be 0 because everything, it seems like this is infinite in the Z direction and we don't see any variation in the Z direction. We notice that the pressure gradient is only acting along the X direction. So what that tells us is that pressure is not a function of Y, it's not a function of Z. That means that this partial derivative of pressure with respect to X is actually a total or ordinary derivative of pressure with respect to X. There were some other things that we ended up looking at when describing the system, but I think these were the most important ones. If my pressure is acting in the X direction, and my plate is moving in the X direction, and my gravity, you can see here, is acting in this direction, which is actually analogous to X and Y, where do you think, in which direction do you think the fluid particles are moving? Or along which axis or axes are the fluid particles moving? So my pressure is exerting a gradient in this direction. This plate is moving in this direction. Gravity is acting in this direction.
Wait, which way is it? Velocity going in the direction?
Well, we don't know. We don't know this. We know that this plate is moving in this direction, just a plate. We know that the fluid that's attached to the plate will also move in that direction, but we have a pressure that's pushing fluid in this direction, but we also have a gravity that's pulling fluid in this vertical direction. So do you think there's fluid movement in the x and y directions? Only in the y direction? Only in the x direction? Which is it?
Only in the y direction.
Okay, it seems like only in the x direction or x and y. I think both answers are logically okay based on the system. Now, you mentioned only x, right? Can you explain a little bit why?
Because we chose the coordinate system of y and x to show where fluid is moving along. I guess.
No, I get it.
I guess in this system, I don't know. I guess I would say because it's too small to show like a like flow going like this. It's wait, it's is it laminar or?
It is, but we haven't really covered that yet, so let's not assume. This will be studied as laminar flow, but right now we don't care about the distinction.
Do it being incompressible?
That is one thing, right? The fluid is incompressible, and you think that may affect, right, whether the fluid moves in the x or y direction. It could.
You have nowhere to go. If it's like layer, it can't go down that way if it's incompressible.
That's good. That's a good way of looking at fluids. So it seems like Will is looking at fluids as if they were layers, right? And if they're layers, then you can't really have that y direction motion because the fluid that the y direction is pushing out has nowhere to go based on that description of pressure and forces. Now, that's a really good explanation, and you're right. However, thinking that it's x and y is actually not such a wrong thought. I mean, if I were to look at it, I would say if there's a force acting with components in the x and y direction, there should be some movement in the x and y direction, right? So I'm not going to say that, oh, you're so wrong, because that's also a good assumption. Now, the question is, how do we know which one of you is right? And we will know by solving this problem. So right now, we know these things, right? We know those things for sure. And it seems like there will be some velocity in the x direction, and maybe, who knows, some velocity in the y direction. So it seems like that's what we know so far. Another thing we see is that if there were no movement in the y direction, then that means that the x direction properties need to be constant. But we don't know if there's movement in the y direction or not yet. So let's just leave it at that here, right? The next thing you want to do when you're dealing with such a problem is to define your boundary conditions. Boundary conditions are these properties of fluids that we know at locations, specifically the boundaries of the control volume, where we actually do know these properties. For example, what's the velocity of a fluid particle that's at the bottom, right here in contact with this plate? 0, right? So we know that for boundary conditions, we know that the velocity in the x direction, u, at my elevation y equals 0 is equal to 0. And what do you think? Remember, this top plate is moving with velocity capital U. So what do you think is the velocity of the fluid particle at the top plate?
U.
Yeah, capital U, that's correct. So we know that U at y equals a is capital U. Now there's a couple of boundary conditions that we'll need to solve problems. We're going to solve this problem with the Navier-Stokes equation, which is a second order differential equation, right? Because it's a second order partial differential equation, we will need at least 2 boundary conditions to solve it. Because it's a second order equation, we'll have 2 constants.
Don't already make the assumption that it's only in the x direction.
But that's if we take only the x direction of the Navier-Stokes equations. The Navier-Stokes equation has 3 components, x, y, and z components, okay? Now in class, we solved only the x direction because we knew that the velocity was only moving in the x direction. But here, I want to know why, okay? This is what we call the no-slip condition, where it says that fluid particles in contact with a solid boundary are going to move at the same velocity as the solid boundary. If the solid boundary is not moving, the fluid particle is not moving. If the solid boundary moves with a velocity u, the fluid particle moves with a velocity u. There's another type of boundary condition called the no penetration condition, which means that fluid particles that are in contact with a solid boundary cannot penetrate that boundary. Unless the boundary is porous, which in this case it's not, right? But if there's a fluid particle in contact with a solid boundary, it cannot penetrate the solid boundary. If it cannot penetrate the solid boundary, then what do you think is the y direction, right, the v, y direction velocity of a fluid particle at this boundary, if it cannot penetrate it? 0, that's correct. So we know that v for y equals 0 is 0. And we can say the same thing here. V, which is the y component for y equals a, is also 0. And that's what we call the no penetration condition. So this is my system. These are my boundary conditions. I think it's important that we understand these before we try to solve this problem. As long as we understand how our system works and what our boundary conditions are, I think then we'll have an easier time solving the problem. If you arrived late, this is the example that we started in the last class that we didn't get to finish. I'm just trying to be a little bit more detailed with the steps that we're taking, okay? So once you describe the system and define your boundary conditions, I think now you can solve your governing equations. And your governing equations are the equations that will govern your fluid motion. In other words, that will determine your fluid motion. Now, at this point in differential form, we've only really covered two governing equations, conservation of mass and conservation of momentum. So we can write down the continuity equation to describe conservation of mass. We can write down the Cauchy equations of motion to describe conservation of momentum. However, because this fluid is incompressible, and let's also say it's Newtonian, then instead of writing the general form of the equations of motion, we can just write the Navier-Stokes equation, which we derived last week. So my governing equations are conservation of mass for an incompressible fluid. You know that for an incompressible fluid, density doesn't change, so we don't even have to worry about the density term. So I'll just write del dot V equals 0. It's continuity. And for momentum, we write the Navier-Stokes equations, which is rho times the derivative of velocity with respect to time equals negative gradient of pressure plus viscosity times Laplacian of velocity plus density times my body force vector. So these are the two governing equations that determine how our fluid will move. This is the continuity equation for incompressible fluids, which determines conservation, or which expresses conservation of mass. These are the Navier-Stokes equations for incompressible Newtonian fluids, which express conservation of momentum. We said that we don't really know if there's movement in the y direction. If you came to class last week, you know that there isn't, but we didn't really explain why there isn't. We just kind of looked at the system and said, it looks like there won't be any y direction movement. But now we're going to see mathematically why there is no y direction movement. Whenever you're solving governing equations, my preference is to start with the easiest equation to solve, which would be conservation of mass, so continuity equation. And because when we solve continuity equation, we may actually get a solution that will help us solve the Navier-Stokes equations, okay? So we're going to start with the continuity equation, which says that the divergence of the velocity field equals 0. Divergence, as you know, is the derivative of u with respect to x, v with respect to y, and w with respect to z. All that equals 0. Based on how we describe the system, what can we start canceling out? Z direction, right? Now, because these plates are infinitely long, we know that we cannot have any changes in that direction of infinity. Because if we were to have any changes in the direction of infinity, that means that at some point in infinity, our changes will be so big that they will be pretty much unrealistic. Now, when that happens, we say that our equation blows up, right? Because we get these results that are incredibly big, infinitely big. And that's not really physical. So because of that, right, our equations do not blow up or cannot blow up, then we should know that when describing the system, that there's also no change along the x direction for any of our properties of velocity, okay? Any of our velocity related properties. Now this one's a little bit harder to understand intuitively. So when we are dealing with problems for an introductory class, I may actually just give you this. But the idea is the more problems we do, the more we'll get used to that condition until we can actually apply it without me needing to give it to you. So based on that information, we get a very simple equation that says dv dy equals 0. And that's a pretty simple partial differential equation to solve, right? If dv dy equals 0, then what is v, the y component of velocity, equal to? How do we solve this partial differential equation? dv dy equals 0. So what is v equal to? Think, if the derivative of your function is 0, what is your function equal to? A constant, right? Some constant. That's correct. Okay. So we solve our equation and then we apply our boundary conditions. So what boundary conditions do we have? We know that v when y equals 0 is 0, and v when y equals a is 0. So when y equals 0, v is 0. But notice that our equation is a constant. It doesn't vary with y, which means that 0 equals c. Therefore, our constant is 0. And if our constant is 0, what is our y component of velocity equal to? V equals a constant, but that constant equals 0. So what is v equal to? 0. So we know that there is no movement in the y direction, which means that the only movement that we need to consider is the velocity along the x direction. And that's what we did last week. Because we were only considering movement along the x direction, we applied the Navier-Stokes equations in the x direction. So I'm going to write momentum here. So to solve the Navier-Stokes equations, well, we just took the x component of these equations, which was rho. The x component would have been dou u dou t plus, and then this is the material derivative, right? So then the convective change in the x direction equals, we have the pressure gradient, but only the x direction component of that pressure gradient. So that would be negative dp dou x. We have viscosity times the Laplacian of velocity, but we only care about the x component. So the x component would be the second derivative of u with respect to x, the second derivative of u with respect to y, and the second derivative of u with respect to z. And then we had our gravitational force, but we only cared about the x component, so I'll just call it gx. And again, at this part, right, I wanted to emphasize this, but this part we already covered it last week in class, so I'm going to try to go a little bit quick. You know that there's no mention of change with respect to time, so this is 0. You know that there is no change in the x velocity with respect to x, so this is 0. You know that there is no v velocity, right? There's no y component of the velocity, so this is 0. There's no z component of velocity, so this is 0. So basically this entire left side is 0. On the right side, we know that there's no change in the x direction, so this is 0. No change in the z direction, so this is 0. And then we end up with a much more simplified equation. Remember, from our description of the system, we found that the change in pressure is actually a total change, right? Not a partial change. So I can write this down as dp over dx. And we also found that this rho gx could be written as negative delta dh over dx. And the explanation for that was covered in last class, okay? But then what does all that give us? We mentioned that by doing a little bit of math, you notice that 0, 0, 0, 0, all this left side is 0. And on the right side, we had negative dp over dx minus gamma dH over dx. Gamma is a constant because it's an incompressible fluid, so we can actually insert it into the derivative, and that gives us the derivative with respect to x of pressure and gamma h. So I'm just going to write it as a derivative with respect to x of pressure plus gamma h. And we had the viscosity times the second derivative of velocity with respect to y. Again, I'm rushing because we already covered this before. And now we ended up with an equation that we could actually solve, right? Dividing both sides by viscosity and moving this term to the other side, we ended up with dou squared u over dou y squared equal negative 1. Oh, I move it to the other side, so it's actually not negative. So positive 1 over viscosity times dp plus gamma h over dx. And we found a couple of things. If there's no change with velocity in the x direction, then dp over dx is a constant. If there is no change in height along the x direction, then d gamma h over dx is a constant. And because this is a Newtonian fluid, then mu is a constant. So this entire side of the equation is actually a constant. Because it's a constant, then that makes our differential equation pretty easy to solve. You may remember that this is essentially a second order differential equation where dou squared u over dou y squared equals a constant. We know that u doesn't change with respect to x, u doesn't change with respect to y, u doesn't change with respect to z, u doesn't change with respect to time, which means that this is actually a total derivative. It's not even a partial derivative, it's a total derivative. So it's actually a second order ordinary differential equation. You haven't taken diffie q? Don't fret. It's actually pretty easy to solve this equation. We solve differential equations through a method called separation of variables. All of your du's and u's on one side, all of your dy's on the other side, okay? So this is d squared u over dy squared. We can actually express this as d over dy because we already know it's an ordinary derivative of du over dy. Notice d squared u over dy squared. All this equals a constant. And now, if we multiply both sides by dy, so move this dy to the other side, and then integrate, what do we get? I'm going to write down all the steps here. We get the derivative, or the change d of du over dy, equals lambda dy, right? I move dy to the other side, and then I integrate. And this integral will give me the integral of d something is just something. So this will be du over dy. And on the other side, the integral of a constant times dy is just the constant times y. Of course, I can't forget my constant of integration a. We don't know what a is yet, but that is there. And then we repeat the process, right? We move dy to the other side. Then we integrate both sides. And we get that u equals lambda over 2y squared plus my constant a times y plus some other constant of integration b. So I have two constants that I don't know. And here's where we left off on the last class. Now what we need to do is to solve this equation. So I'm going to rewrite the equation here. We ended up with an unknown equation, u equals lambda over 2y squared plus ay plus b. And we don't know what a is, we don't know what b is, but we do have our boundary conditions. So whenever you get to a form of an equation that deals with unknown constants, that is when you can apply your boundary conditions. So I'm going to write down apply your boundary conditions. What do we have? We get when y equals 0, u equals 0. Is that correct? So let's apply that. When y equals 0, u equals 0. So we get this equation. When y equals 0, u equals 0. So I write it down. U equals 0. Here I get lambda over 2 times y squared, but y equals 0. So what is this term equal to? 0. Here I get ay, but y equals 0. So it's just 0. And here I get my B term. So this tells us that my constant B equals 0. Now I can apply my second boundary condition. When y equals a, u equals capital U. That's the velocity of the top plate. So let me apply that. When y equals a, then u equals capital U. So capital U equals lambda over 2a squared plus my unknown constant of integration a times my a plus b. But we already know that b equals 0, so we don't even have to include it here. So this is just plus 0. And now I can solve for my unknown constant a. I get that a will equal u minus lambda over 2a squared, but I have to divide both sides by a, so u over a. And this is my a term. And now I can finally solve this equation. I get that my velocity u equals lambda over 2y squared plus ay, but we know that a is equal to all this, so I'm going to write it down, u, capital U over a, minus lambda over 2a, multiplied by y, plus b, but we already know that b equals 0. And this is my equation. I mean, up to this point, we're good. We can actually organize it a little bit better. And just to make it sound nicer, let's see. We have lambda over 2. I'm going to factor that out. I get lambda over 2 y squared minus ay plus capital U over a times y. And of course, we know that lambda was equal to this entire term. So I can write it down. Lambda equals 1 over viscosity. So 1 over viscosity. I have the 2 here times the pressure and gravity gradient. So, and at this point, really, I'm just organizing it to make it look nicer. That's really all I'm doing. And here is an exact solution to the Navier-Stokes equation for the case of flow between two infinitely long parallel plates. So notice that we first had to describe the system, and really this is going to be the hardest part because this is the part that requires the most experience, right? The more you practice, the better you'll get at describing the system. We said boundary conditions. Again, with practice, you get better at them, but the two types of boundary conditions that you should always look at for are no slip and no penetration. There are others, right? Open channels, pressure at the surface is atmospheric. You have infinitely long channels, the velocity or any change at the infinite is 0. So you're going to get used to them. But for now, no slip and no penetration will be the ones that you want to solve for, always look for. And finally, we solve the governing equations. Start with mass. Mass will be pretty easy to solve in most cases, then solve momentum. The reason I wanted to make this review is because in order to study pipes, we need to make sure that we understand how to solve these types of equations. So this week, we're going to start a new topic, which is called flow in pipes. If you saw the changes to the calendar, you know that we were originally going to start with internal flow, so 1 week of this theory, and then pipe systems, so 1 week of the applications. But because we're a little bit low on time, we're going to try to focus all the theory today and all the applications on Thursday. So let's talk a little bit about flow in pipes. Now, when we were talking about whether the fluid will move in the x direction or the y direction, Will, you mentioned something interesting. You asked if the flow was laminar, right? Can you explain to me what you mean by that?
Meaning that there is no, I think it would mean there would be no change in the y, therefore if everything's on a streamline. Yeah, if everything's on perfectly on the streamline.
Yeah, that's very close, right? So when your flow is laminar, what Will means is that you can pretty much identify the streamline of the flow, right? It has a very defined streamline. There's a little bit more than that. I would say when our flow is laminar, the streamlines don't intersect, so there's no mixing. But then we need to first define what does laminar mean. Conceptually, you think of laminar, and you think of these layers, right? In fact, the word lamina is just a flat layer. Okay, so you think of laminar, you think of layers. But we need to have a more rigorous definition of laminar. Especially if we're going to start dealing with numbers, we want to make sure we have a strong mathematical definition of what laminar means. So in order to define laminar flow, let's identify a new term called the Reynolds number. This Reynolds number is a dimensionless term that describes the ratio of inertial forces to viscous forces. Whenever you have fluid in motion, you have all these types of forces acting on them, right? You have forces from the movement of the fluid itself, right? Like the inertial forces. You have forces from the friction, right? Those are your viscous forces. You have pressure forces, right? You have gravitational forces, yeah?
I'm wondering, right, does this mean that in this system we would only have initial conditions without any boundary conditions?
What do you mean?
From PDQ, if you have like a vector field, you set an initial condition, you have an equation, and another one you have a different equation, but those equations will never intersect. So I would think that the only way for them to intersect would be adding a boundary condition that would cause them to.
But here our equation is for the velocity, and each velocity at each point y is its own streamline, right? So you actually have one equation for each of the layers of fluid. So in this case, I don't think that would apply so much. This is a little bit simpler than the example that you're going to be dealing with at DFQ, I would say. So in this case, one, we do need boundary conditions, but two, we don't really need a different equation for each fluid particle or a different equation for each streamline, because our equation actually gives us, right, with respect to y, what is the velocity at that streamline. So in this case, I think we're good. We won't be on Thursday, but for now we're good, okay? So whenever you have fluid particle, you have all these forces acting on it. Forces from pressure, forces from friction, forces from gravity, electromagnetic forces, even inertial forces. Now the Reynolds number is a dimensionless term that seeks to look at the ratio between your inertial forces and your viscous forces. So then how do we quantify these forces? Well, inertial force, when you hear inertial force, what's that looking at? When you hear the word inertial force, what do you think we're looking at in the fluid particle? The inertial force, it looks at the particle's inertia, right? Which is a function of its mass. That's correct. Inertia, right? You may remember Newton's law of inertia. An object in motion stays in motion. An object at rest stays at rest. Inertia just gives you that fluid particle's tendency to remain in its current state. In other words, if the fluid is moving at a fast velocity, inertial force will be its tendency to remain at that fast velocity. If the fluid is at rest, inertial force will be the tendency of the fluid to stay at rest. Now we can quantify this inertial force. And I'm going to try to run quickly because this is really not a dimensionless class, at least not yet. So we can quantify these inertial forces by looking at the mass and velocity. This is momentum. And then looking at the change of velocity along a length of movement. In this case, we can just call it ds, so along a length along the streamline. S is just the dimension along the streamline. So that's pretty much inertial force. Now, we know that mass, at least in dimension, if it's a really small particle, mass is just rho dV, right, for a very, very, very small particle. We know that for a very, very small trajectory of motion, velocity is just length over time, right? And we know here, derivative velocity with respect to s is simply velocity over length. So we can approximate, and I want to be careful here. We're not saying this is equal to, but this is pretty much approximate to density times some volume of the fluid particle times the velocity over a length. And that length is along a streamline. So here I'm kind of trying to focus on the dimensions of this equation. And if we were to solve this a little bit further, then we would know that this is just length cubed over length is length squared. What am I missing here? Yeah. And then velocity times velocity is velocity squared. So this is just density times length squared times velocity squared. Up to this point, is everything I'm doing making sense to you? We know that this is inertial force. Mass, we can treat it for a very small particle. We can approximate as density times volume. And volume is just length cubed. Sorry? No, this is actually a force, right? Because you see it's mass, velocity times v over length. This is time. So velocity over time is simply some acceleration, some mass times acceleration. It's a force. Okay? On the side of viscous forces, we know that force is a stress times an area. Is that correct? Stress is force over area. Think of pressure, normal stress, force over area, right? So stress is force over area. So force has to be stress times area. Now here we're looking at a fluid moving along a streamline. So we're only focusing on the direction of the streamline. And we know that this stress can be quantified by Newton's law of viscosity, which we covered on week number 2, several weeks ago in this class. And that Newton's law of viscosity said that the shear stress was equal to viscosity times du over dy. And of course, this is multiplied by an area. Now I can approximate this, right, as my viscous coefficient, so my viscosity, du over dy. U is my velocity, and if x is the direction of the streamline, then u is simply my v, my velocity along the streamline. And y is a length. And area is a length squared. All this leaves me with is viscosity times velocity times a length. So these are very, very crude approximations, right? We're simply trying to approximate these forces on the basis of their dimensions. But then where does that leave the Reynolds number? So now we see that this Reynolds number, since it's a ratio of inertial forces to viscous forces, should be equal to my inertial force term, which is density times length squared times velocity squared, over my viscous term, which is viscosity times velocity times length. I'm going to write length times velocity, flip those two terms around. Ethan, what does this give me?
Rho LV over mu.
Exactly, density, some length, some velocity, or viscosity. Let's remember, you may have forgotten, but let's recall that the term kinematic viscosity is simply your dynamic viscosity over density. Okay, so kinematic viscosity is mu over density. And this length is what we call a characteristic length. And that characteristic length is a length that's going to show you or define the geometry of your flow. Combining all this information into one place, we get our definition for the Reynolds number, which, as you can see here, is velocity times the characteristic length divided by kinematic viscosity. And that's the definition that we're going to use for the Reynolds number. Velocity times characteristic length times kinematic viscosity. Velocity, I think, is something that you can identify pretty easily. And kinematic viscosity depends on the properties of the fluid, depends on the temperature of the fluid and the type of fluid that we're dealing with. This characteristic length, you'll see that it depends on the shape, the geometry of flow. Now, calculating or determining that characteristic length is, it really depends on the type of problem that you want to solve. So just to make things simpler for today's lecture, let's look at pipes. For pipes, this characteristic length, what do you think it is? If you have a pipe, what dimension along that pipe do you think can actually give you everything you need to know about the pipe? Its radius, right? Or in this case, it'll be its diameter. Either way, right? That length pretty much tells you what the pipe looks like. If I have any pipe, and I give you the radius or the diameter, then you know what the pipe looks like. We know it's circular, so the characteristic length will be the diameter. Therefore, the Reynolds number for a pipe should be equal to velocity times diameter times kinematic viscosity. This kinematic viscosity, remember, is a Greek letter nu. It's not a V, it's a Greek letter nu. The reason we are explaining this is because when these viscous forces dominate, right, then the flow will essentially behave like this equation that we derived. Notice that this equation, the viscosity, plays a key role in the velocity. However, when the inertial forces dominate, you'll see that the flow will actually be determined by the velocity of a fluid particle at a particular point in space and time. So this week, we're going to look at those two different scenarios. What happens when these viscous forces dominate? What happens when these inertial forces dominate? The range for which we can say that viscous forces and inertial forces are dominating is a little bit varied, right? Different scholars, different engineers will have different opinions on what that range is. For me, if your Reynolds number is smaller than 2000, then it is safe to say that these viscous forces are dominating. And when these viscous forces dominate, we say that we have laminar flow. If it's greater than, let's say, around 4000, then these inertial forces are dominating. So we say that we have turbulent flow. And if it lands somewhere in between, then I would say your flow can behave as either. So we say that we are in the transition or transitionary regime. Now these numbers really depend on the type of flow that we're studying and the type of fluid that we're using. You'll see that for some fluids, you can actually maintain laminar flow even with a Reynolds number as high as 10,000. For others, Reynolds numbers as low as 2,000 already start giving a turbulent flow. So there is no standard set of numbers that I can say, memorize these numbers because they will be valid for any type of fluid, any type of flow. It really depends on the type of flow that you're studying. Now, because we are more of a comprehensive university, our job is to prepare you for industry. And in industry, we need to figure out what are the types of flows that you will be dealing with. Civil engineers have it easy. We deal with water, we deal with air, and we deal with water mixed with poop in the case of sanitary design, right? So it's a pretty simple set of fluids for which most of our flows are actually turbulent. Mechanical engineers, you have a little bit more variety, right? You're going to deal with water, you're going to deal with air, you're going to deal with propellants, you're going to deal with gas, different types of gases, you're going to deal with gasoline, you're going to deal with oils, you're going to deal with coolants, you're going to deal with a lot of different types of fluids, most of which are Newtonian, and about half of which will be in the laminar regime. So we're going to have a good base on both laminar and turbulent flow in order to say that we are fully prepared for what we are going to see after graduation. I'm going to keep these, I'm going to try to use this range for my class, but remember that this range actually varies depending on the fluids that you're using and depending on the type of flow that you're trying to study. So let's keep that in mind, right? This is not written in stone. These ranges really vary. It can get frustrating when you look at different fluids book and each book gives you a different range and says, this is it. It's not it, right? It really varies. So if you pick up two different fluids books, you'll see that they'll have two different types of, or different types of ranges for what constitutes laminar flow, what constitutes turbulent flow. There are some universally accepted ranges. For example, anything less than 100 has to be laminar flow. You cannot have turbulent flow with a Reynolds number of 5. Anything higher than 10,000 has to be turbulent flow, right? You cannot have laminar flow with a Reynolds number of 1,000,000. So there are some accepted things, but we're going to learn about those as we keep working on problems in this class, okay? Now, when viscous forces dominate, then that means that we're dealing with laminar flow. And my hope is to use the remaining half hour of this class to derive some equations that give us the velocity profile of laminar flow. So let's look into that. We know that when viscous forces dominate, we have laminar flow. Laminar flow means that the viscosity of the fluid will be enough to determine the velocity profile. In other words, we don't really care about the velocity of the fluid as it flows through the pipe, because that won't change the velocity profile. In other words, as we saw in that previous exercise, the velocity in the x direction did not change. It was just constant through the x direction. It only changed based on the distance between the particle and the boundaries. That's essentially laminar flow. And what we're going to do now is we're going to try to solve the Navier-Stokes equation for laminar flow in a pipe, because this week, as we said, we're going to focus on flow on pipes. So let's spend whatever time remains in this class finding an exact solution for the Navier-Stokes equation to give the velocity profile for a laminar flow in a pipe. Now we want our equation to be as generic as can be. So just for the purpose of being generic, we're going to assume that the pipe is inclined at some unknown angle theta. We know that fluid travels in this direction. I'm going to say that this pipe has a radius of r, capital R. Or you can also say that it has a diameter of capital D, whichever one you prefer. You know we have a pressure gradient, but from the previous exercise, we found that the pressure gradient is constant. So we know that the flow here is laminar, incompressible, and Newtonian. Okay? Now this is all the information we know. Very, very similar to the previous exercise, except that in the previous exercise, we were dealing with two infinitely long plates. Here we're dealing with a pipe. Okay, so this is the pipe, circular pipe. How do you think our final answer will change? First off, how is flow in a pipe different from the flow between two infinitely long parallel plates? Any differences other than geometry, but any differences in the velocity that you can think of?
It will vary in the three directions.
Okay, so there is some variation.
It will be the same as it would have been if it's a circular pipe. It will be the same as it was for the y direction, because you're essentially just removing the x coordinate by curving it.
Okay, I like what you're saying. Just for reference, you're saying x coordinate is essentially the direction of flow?
X will be the same.
Okay, and then you have your y and z. And you're right, there will be some variation along actually any axis, right? If you look at the pipe, you have friction all around your flow, so you're going to have some variation all around. When I was teaching statics a few weeks ago, we wanted to find the centroid of a circular shape, and we saw that in order to use Cartesian coordinates x, y, and z for circles, we ended up with these really, really hard to solve integrals, right? Integral of 1 minus x squared, or square root of 1 minus x squared or something. It's very, very hard to solve integrals that ended up with hyperbolic signs and all these things. So we tried to use a different coordinate system called polar coordinates. But when I recommended that, nobody knew where polar coordinates were. So I realized, either I'm in trouble or somebody's not doing their job here at Kennesaw. So I'm not going to assume that you know what these coordinates are. I'm just going to explain to you. There's different ways of writing down coordinate systems, right? And what we've been using all this time has been the Cartesian coordinate system. Do you know who it was named after? René Descartes, the founder of modern philosophy, right? I think, therefore I am. So the Cartesian coordinate system, which was given to us by Descartes, essentially looks at a point in space as a function of three distances, x, y, and z. Those three distances are orthogonal. That means normal, perpendicular to each other. So in the Cartesian coordinate system, we would have 3 coordinates, x, y, and z, that would help us locate a point in space. And those 3 coordinates would be orthogonal, that is perpendicular, from each other. But there's other ways to locate points. That's not the only way. Think of spherical coordinates, where we can locate a point as a function of its radius, if you were to look at it as if it were a circle, its radius, as well as the angle from 2 different planes. You have radius and 2 angles, you can locate any point in space as well. For this pipe, it seems like we would benefit from using polar coordinates. Polar coordinates are radius and angle. However, because this is a 3-dimensional pipe, we're going to have to add a 3rd dimension, which we call x, which is a direction in the direction of flow. When we have a system that consists of polar coordinates in one plane and then a length coordinate, we call those cylindrical coordinates. And how do cylindrical coordinates work? We define points in space as functions of some length coordinate, some radius, that is distance from the center, and then some angle theta. So as long as you have an x coordinate, a radius coordinate, and the angle theta, you can locate any point in this pipe. If your x is from here to here, then you know that your point will start here. Your radius will tell you the distance from this point, right, the distance, and then your theta will tell you in which direction to orient that distance. Okay, so that's cylindrical coordinates. When we're solving equations for pipes, cylindrical coordinates is the best thing you can do. Because if you try to solve using Cartesian coordinates, you'll see in Cartesian coordinates, you know that flow moves in this direction, and flow varies with the distance from the wall of the pipe, right? That means that in Cartesian coordinates, my velocity will vary with respect to x, y, and with z. We're going to end up with a very, very hard equation to solve. But if we're looking at polar coordinates, we know flow travels in the x direction. When it comes to polar coordinates, my velocity will vary with respect to only the radius, right? Because the distance from the center is the only thing that tells me that the velocity is changing. The velocity does not change with respect to angle because our system is symmetrical, which means that as long as you're at the same distance from the center, you'll have the same velocity regardless of where in the pipe you are, right? So with polar coordinates, my velocity only varies with respect to my radius coordinate r. Coming up with these coordinate transformations is not something easy and not something that I care to teach right now because we're a little bit out of time. But I'm going to recommend you to read some literature on coordinate transformations just for your future classes. You're not going to really need that much for my class, but you will need them for future classes. So we'll talk about that later. For now, let's try to solve this system in cylindrical coordinates. We mentioned that we first would like to describe the system, right? So what can you tell me about this system? And I'm just telling you now directly, flow is traveling in this direction. We already know that for laminar flow and all these stipulations put together, flow will really only travel in the x direction. So what can we say about this system? When you describe the system, you want to talk about velocities, you want to talk about changes, anything you can think of, right? Let's see. If flow only travels in the x direction, right, which we can call Vx, then what do you think is the velocity in the radial direction? Any velocity of the fluid moving away from the center? Zero. What about the velocity in the angular direction? Any velocity of the fluid rotating? Zero, that's correct. So VR. Yep. VR and V theta are both zero. Correct. This flow will have no vorticity, right? So del cross V equals 0 as well. So we know that from our system. What else do we know? We already know that this pipe, if it's an infinitely long pipe, which we can treat it as such, we know that for the equation not to blow up, then the change in velocity with respect to x has to be what? If the pipe is infinite and the equation cannot blow up, what is the change in velocity along the direction of velocity? Zero, right? There cannot be any change. Good. And because of that, right, because the velocity only moves in the x direction, we know that the pressure gradient along the x direction is a total derivative, not a partial derivative. So we have a very similar scenario, okay? Do you understand what I mean when I say Vx, Vr, V theta? Yeah? Okay. So
Do you have to say Vx here for the partial?
you can just call it velocity because there is only one velocity component. But I do want to distinguish it from Vr and V theta because this is velocity. This is the movement of the fluid away from the center. This is the movement of the fluid around the pipe, right? Rotating on the pipe. So we want to distinguish those three velocities, okay? But I'm going to call it Vx. Sometimes people call this the z-axis. I'm calling it the x-axis, okay? So we described our system. Let's look at boundary conditions. What do we know about this pipe? What do we know about boundary conditions? The velocity varies with respect to, in this case, I guess it has to vary with respect to radius, right? So what's the velocity? And radius is a coordinate measured from the center, right? If radius is a coordinate measured from the center, what's the velocity of the fluid when my radius equals capital R, the radius of the pipe? Zero, right? Good. So for boundary conditions, we know that Vx, when my radius equals capital R, is 0. I mentioned that if we're going to solve a second order differential equation, we need at least two boundary conditions. Now here we have a problem because Vx when R equals radius equals 0, and that really pretty much covers the entire boundary. So we need something else to deal with. What? We can, but we don't really know anything about it until we solve the velocity profile. So I'm going to help you a little bit here. Well, if we look at this,
85 from the homework where we're not given our boundary condition for the velocity equation at least. You receive two constants, and your constant could have to be solved using a relation between the tensor and the.
Yep. But we're already applying that tensor in the Navier-Stokes. That's the thing. We're already applying that, right? We're not really adding any equation there. We're pretty much using what we already have. When you get to this point, like Will said, you can look at your stress tensor. But if you're already using your stress tensor, which we are in the Navier-Stokes equation, you need to try to visualize what this velocity profile will look like. Chase, what do you think the velocity profile will look like? In other words, if I were to plot the velocity of each particle from here to here, what do you think that would look like? We know that the velocity at the walls is 0. So what do you think that will look like? Kind of like a parabola. Okay, so something like this? Okay. Where do you think the highest point will be in the velocity, the highest velocity? Okay, so we know that at the middle, my velocity is Vmax, okay? And how does that help us? If my velocity at the middle is a maximum value, then what do you think is the derivative of that velocity with respect to R at R equals 0 at the middle? What's the derivative? If that's a maximum value, what's its derivative? What's the derivative of any maximum or minimum value? 0, right? So we know that the derivative of velocity with respect to R when R equals 0 is 0. And then we have our two boundary conditions. Takes a little bit of intuition here, but I think we can all see it, right? We can all see how the velocity kind of behaves like a parabola and why the maximum velocity will go through the middle, right? Because the middle is actually at equal points, right? At an equal distance from every single point in the wall. which means that that is your maximum velocity. That is the highest you can go because that's the less friction that you are going to experience. So we came up with our two boundary conditions. I agree the second one, it takes a little bit of, looking at it, trying to figure out what's going to look like. But I think those are very good boundary conditions. Finally, after we define our boundary conditions, we can solve our governing equations. We had mass, we had momentum. We would use conservation of mass to figure out that VR equals 0. So we don't need to go over it. Yeah? Because in the last example, the maximum velocity is not in the middle. Right? If there was only pressure, then the maximum velocity would be in the middle. Yeah. But here we have an extra term here, right? This is moving. So our velocity profile is a combination of pressure and this velocity profile. So it wouldn't really be in the middle. That's why we cannot do it. If I would have told you the two plates are still static, then yes, we can do that too. Okay? So we solve our governing equations. We apply conservation of mass to find out that this is 0, but we don't need to do this because we already know just from looking at the system. So we can go straight to solving the conservation of momentum. And again, normally I would take longer to teach this section, but we are in a little bit of a time delay. So just take my word that this is 0, and let's just go straight to solving the Navier-Stokes equations. The Navier-Stokes equations, you may recall, I like to write them over and over again because the more I write them, the better I memorize them. And that way, if I memorize them, it's a lot easier for me to use them, okay? Here, we're going to look at the components of these vectors in cylindrical coordinates. So we're going to have to write our Navier-Stokes equations in cylindrical coordinates. And in this case, because we only want the velocity in the x direction, we only need the component in the x direction. So in cylindrical coordinates, specifically in the x direction, you can apply some coordinate transformations and you will arrive at the following form of the Navier-Stokes equations. You have your temporal change plus your convective change all this equals my pressure gradient, but we only look at the x direction, so dou p dou x. My viscous gradient, that's my Laplacian of velocity. Space, good. And finally, my body force. So this is just the Navier-Stokes equation, but in cylindrical coordinates. So you'll see that we kind of came up with these additional terms, v theta over r, 1 over r, 1 over r squared. This is just a result of the coordinate transformation. We don't really have enough time to go over the entire coordinate transformation, so let me just give you an example. If you're converting from Cartesian to polar coordinates, right, you know that polar coordinates is radius r and angle theta. So in Cartesian coordinates, your x coordinate is r cosine theta. Your y coordinate is r sine theta. So it's a similar thing. Then essentially, we're applying those same transformations, but in 3 dimensions, in other words, in cylindrical coordinates. And this is our equation. Now, this is not a class about coordinate transformations. So what I do want to get from you is an understanding of how to solve this equation after I give it to you. So after I give you the Navier-Stokes equation in cylindrical coordinates, You look at the equation, Ethan, what's the first term that you think we can cancel out of this equation? The time, right? There is no change with respect to time. We have what's essentially a steady system. So we know that any change in velocity with respect to time equals 0. Chase, based on our description of the system, what else can we cancel out?
Radial velocity.
All right, yeah, we get that VR from the description. We get VR equals 0. So wherever we see a VR, we know that it's 0. Is that correct? Okay. Do you think we can cancel this term out, Chase?
Yes,
That's correct. And then we also know that Vx over derivative of Vx over x is 0. Good. Mohammed, what else do you think we can cancel out based on this description of the system? What else can we cancel out? Okay, well, it's a constant change, right? So you're right, this is not a partial change, it's a constant change. Let's be careful not to cancel it out. We just know it as constant. Does my velocity change with respect to theta? No, right? It's axis symmetrical, right? Symmetrical about the axis. Does my velocity change with respect to x? No, that's correct. So this leaves us with a simpler equation that we can now solve. Let's see, 0, 0, 0, 0, all the left side is 0, so we get 0 equals. And on the right side, what do I have? Let's see, I have negative. We know that this is a ordinary derivative, right, a total derivative, so I'll just write negative dp over dx plus viscosity. I'm left with these two terms, dou squared vx over dou r squared plus 1 over r, dou vx over dou r, 0, 0, I don't care about them, plus, from our previous exercise, we already figured out that this is just gamma dh over dx, and it's a negative value, so, and this was from our previous exercise, okay? We don't have to explain it again. Okay, notice that this is starting to look like our previous exercise. I mean, there's still some work we can do, right? There's still some differences, but it is at least starting to look like it. So let me just reorganize this. Move gamma inside the derivative. We have d over dx, so they're both constant. I'm going to move them to either side. I'm going to divide both sides by viscosity. And I end up with, once again, 1 over viscosity, d pressure plus gamma h over dx. This is actually the very, very same constant term that we had in the previous exercise. So no differences there. That's good. But our right side starts to look a little different, right? On the right side, we get dou squared vx over dou r squared plus 1 over r dou vx over dou r. So there's a little bit of work we may have to do here. But essentially, we have this equation. Now, how we solve this equation requires a little bit of math knowledge. But because we're short on time, I'm going to try to force that math knowledge out of you, okay? So I have a quick mathematical question. What is, so these are just notes. What is the derivative, the partial derivative with respect to r of r times the derivative of vx with respect to r? Just mathematically, using the product rule. Does anybody remember the product rule? The derivative of f times g is f times the derivative of g plus g times the derivative of x, the product rule. So using the product rule, what is this derivative equal to? Well, the product rule tells me that the derivative of two functions multiplied together is equal to the first function plus the derivative of the second one times the second function plus times the derivative of the first one. Does that ring a bell, the product rule? Okay, so let's do that. In this case, what's the first function? We have two functions here. What's the first one? R. Okay, so the product rule tells me that this derivative will be the first function r. What's the derivative of the second one? What's the derivative of a derivative?
Derivative.
Yeah, second derivative, right? Okay, plus the second function, dv over dr, times the derivative of the first function. What's the derivative of r with respect to r? Sorry? 1. Okay. So this is equal to this, right? So if you look at this expression, and then you look at what we have on the right side of this equation, what's missing?
So 1 over r.
1 over r, right?
Same if you multiply.
Exactly. Multiply everything by 1 over r, or divide by r, and we essentially get this expression. So the reason I'm saying this is because this allows me to write down the equation, right, as 1 over r, the derivative with respect to r, of r times the derivative of vx with respect to r. From our first exercise, you may remember that the viscosity, pressure, and gravitational terms were constant, right? So we're just going to call it lambda, where lambda is a constant. That's all you need to know. Lambda is a constant. Now it's 3:15. We're out of time. But why don't we do, just for a little bit of homework, why don't you try to solve this equation? So we got this far. Try to solve this equation knowing that this is a constant. And let's see on Thursday if we can, or I guess on the review session or next week, if we can get the same results, okay? So let's stop the class here, solve this equation. Notice that you may have to move stuff to the other side. You may have to integrate twice. You may have to do all these different things, okay? But yeah, try to solve this equation, and we'll see you next class, I guess.